All right, so we're going to introduce a little bit more terminology here. So we'll introduce two definitions, and then we're going to prove a result that relates to the definitions. Okay, so a finite extension. Well, what should a finite extension be? It should be a field extension. Oops, L over K, where the degree of L over K is finite. And the way we represent that is saying less than infinity. So that's a finite extension. Almost, all of our simple algebraic extensions are finite. So uh, we're mainly going to be considering finite extensions, with the infinite ones being reserved for examples of interesting things happening. All right, so the next definition is as following. An extension, L over K, is called algebraic. So we know what it means for elements to be algebraic. They satisfy a polynomial equation over the ground field. So the field extension itself is algebraic if all of the elements are algebraic. So if every element of L is algebraic over K. Let me point out something here. Using the definition to prove an extension is algebraic is a terrible idea. And let me show you that it's a terrible idea. So example. Where's my example color? Here we go. So I claim that Q adjoin root 2, this is the most innocent extension that we have, right? Q adjoin root 2 over Q. This is the simplest non-trivial extension in this class, is this extension, or adding any root. So I claim this is, well, it's finite. That's obvious. It's degree 2. So we're not going to, that's a check. There's nothing to do here. Okay, sure. But it's also algebraic. All right, so let me just show you why it's a terrible idea to use the definition. And keep in mind, this is the simplest non-trivial extension that we have. Okay, so yes, it is true that root 2 is algebraic. But that's not what the definition says. The definition says we have to check every single element of the big field satisfies a polynomial equation over the small field. So let's do that. Let's take any a plus b root 2 in Q adjoin root 2. To show Q adjoin root 2 over Q is algebraic, we need to show that a plus b root 2, where we don't know anything about a and b, satisfies a polynomial equation over Q. That's what we need to show. Okay? All right, so somehow we have to cook up a polynomial that this one satisfies. So there's a standard way of going about finding polynomials that a certain number satisfies. So what we're going to do is we're going to set x equal to a plus b root 2. All right, and then we're going to look at x minus a, so subtract a from both sides. That's b root 2. Now, one of two things is true here. If b is 0, then the polynomial is t minus a. Otherwise, b is not 0. Right? If b is 0, then there actually is no root 2 portion. So the polynomial that should be satisfied is just t minus whatever rational number you're adding. But if there is a root 2 portion, so b is not 0, then we can square both sides. And if we square both sides, we get x minus a squared is 2b squared. And so if we then subtract that over, we have x minus a squared minus 2b squared is 0. And technically we're done here, but I'm going to multiply everything out. We have x squared minus 2ax plus a squared minus 2b squared is 0. And so the polynomial that the polynomial is going to be t squared minus 2at plus a squared minus 2b squared. And in fact, this is the minimal polynomial of a plus b root 2 when b is not 0. Why is it the minimal polynomial? Well, root 2 is not in the ground field, so the minimal polynomial has to be a degree at least 2. And here's a polynomial which is monic of degree at least 2. Okay. Now, this was a lot of work by comparison to a lemma that I'm going to state here in a second, right? This was like non-trivial. Now take a moment and just imagine what this would be like if I was to ask you the following question. Is the extension Q adjoin root 2 root 3 over Q algebraic? Well, certainly root 2 and root 3 individually are, but how would we take a random, like what polynomial do we cook up where we take a random element here and we, like what polynomial does a random element here satisfy? That's what I want to say. And you could sit here and you could play the same game. You could write out a general element of that field, some p plus q root 2 plus r root 3 plus s root 6. And you could sit here you could subtract the p over, and then you can go on the taking powers game. A general element is going to satisfy a polynomial of degree 4, though, and it just becomes very computationally involved. It was already somewhat computationally involved for the degree 2 case by comparison to what I'm about to say. Okay, so the answer is yes, it is, but we're not doing it. We aren't brute forcing it because it's not gonna. It would be an hour-long video. We could do it. We believe in ourselves. We're not brute forcing the computation. All right, I guess that's the answer, right? Okay, so let's state a lemma. And the lemma is going to make our lives way easier. So what does it say? An extension L over K is finite if and only if L is obtained from K by adjoining finitely many elements and each of those elements is algebraic over K. So this is saying that it's finite if and only if finitely generated by algebraic elements over K. That's how I remember it, at least. So it's not necessarily true that algebraic extensions are finite, but if you're finite, you have to be algebraic and generated by finitely many elements conversely. Okay, there are algebraic extensions that are not finite, and we'll probably see an example of that in class. All right, so let's prove it. So we proceed by induction. All right, and what we're going to do is we are going to first show the forward direction. Actually, let me be a little more clear. So we begin. Actually, we're going to show the backwards direction by proving the backwards direction. That is, if L is K alpha 1 alpha R, and each alpha I is algebraic over K, then L over K is finite. Okay. I actually don't think we need induction here, so we apply the Tower law. Guess that's a capital here. And when we apply the Tower law, the degree of L over K is the degree of K adjoin alpha 1 over alpha R over K adjoin alpha 1 over alpha R minus 1. And then we keep going until we get alpha 1 alpha 2 over K adjoin alpha 1. And then finally K adjoin alpha 1 over K. So we just keep adding in elements to K, building it up. All right, since alpha I satisfies a polynomial equation over K, it also satisfies 1 if we add more numbers. Right? If I give myself more numbers, I have probably a smaller degree polynomial equation I can satisfy. So alpha I is algebraic over this field K adjoin alpha 1 to alpha I minus 1. So each time we add a new element, it's algebraic over the field that we're at. All right, so by the relation to the degrees of minimal polynomials, each one of these extensions, alpha I, sorry, each time we add in a new alpha, it's all finite. Right, because we're adding in an algebraic element, and the degree of that extension is the degree of the minimal polynomial over the field that we're adding it to. So each one of these fields involved in this product up here, each one of the degrees involved in this product up here is a finite number. So thus, the degree of L over K is a finite product of finite numbers, and hence finite. All right, great. So that's the backwards direction. We're now going to go for the forward direction. So for the forward direction, suppose that L over K is finite. We show there exists finitely many alpha 1 through alpha R in L, algebraic over K, such that L is K adjoin alpha 1 alpha R. Okay, so we can obtain L from K by adding in finitely many algebraic elements. All right, so how does that go? Well, since L over K is finite, let's say it's R less than infinity, there exists a basis alpha 1 through alpha R, and this is a K basis. Oops. And that's the definition of degree. It's the size of a basis. Okay. Well, every element in L is a K-linear combination of the basis. So since it's a basis, L is certainly generated over K by the basis. It suffices to show that each of the alphas is algebraic. Therefore, the book is really terse with the proof here. I feel like a lot more needs to be said. So they, in the book it says each alpha j is clearly algebraic. Yeah, I mean, I guess, but I think it still needs to be said. So, why is each of these alphas algebraic? So we claim each alpha is algebraic, and that will complete the proof. And then this video. Sorry, it's going a little long. Well, we know that the degree of L over K is R. So if we look at 1 alpha I squared, alpha I cubed, all the way to alpha I to the R, this is a collection of R plus 1 elements of L. And any collection of R plus 1 elements of L is, well, it's bigger than the size of a basis, so there must be a dependence. So that is, there exists K0, K1, all the way up to Kr in K, such that what? Well, K0 times 1 plus K1 times alpha I plus K2 times alpha I squared, all the way up to Kr times alpha I to the R is 0, where not all of the K's are 0. Okay. Now it can't be that K1, K2, all the way up to Kr are 0, because then that would say that K0 times 1 is 0, and 1 is not 0 in a field. So in fact, some of these higher K's have to be non-zero as well. Well, then what? Then alpha I satisfies the polynomial K0 plus K1t plus K2t squared, all the way up to Kr t to the R. Polynomial equation, and this is a non-trivial polynomial equation. So alpha I is algebraic. And that completes the proof.